Hello, my name is John Ribera, and this video is going to provide an overview of my senior project, which is on pressure switch lifecycle testing at various environmental conditions. This project is going to outline the process of developing a high-speed test and measurement system for automatic, simultaneous data acquisition of semiconductors actuation thresholds in a controlled environmental chamber. The purpose of this particular environmental test is to validate that Roscoe switches perform the quality standards specified in the product catalog. The system will be designed to test the new product line, Project Semi, as well as be used in replace of the older procedure for all other product lines. As for the rest of the video, we will be going over an introduction and background of Roscoe and environmental testing, the problem statement, key applicable classes, the assumptions, the systematic approach and methodology, and then we will look into the proposed solution and design of the project, along with economic justification, environmental impact, and we will also look at opportunities for improvement. So who is Roscoe? Roscoe Sales and Marketing began as a screw company and eventually evolved into a manufacturer of pressure and vacuum switches, transducers, and transmitters. Created and maintained by the Way family, the company's name is an acronym for Way Automatic Screw Company. Today, Roscoe supplies the file suppression, medical, semiconductor, and defense markets in addition to providing solutions for industrial applications such as automation. In 2013, Roscoe upgraded their environmental testing equipment with the purchase of an S-Spec Platonia Series environmental chamber for the purpose of testing the quality requirements of their products. Roscoe has recently been contracted by a successful manufacturer of wafer fabrication equipment, Lam Research, to design a new product line named Project Semi. Because of the high quality demands required by Lam Research, the Project Semi coordinators must design a process to test Roscoe's new product line against Lam Research's stringent standards. The success of this project will provide Roscoe more opportunities to satisfy its customers who require similar environmental testing procedures. The program will also enable Roscoe to run lifecycle testing, accuracy testing, repeatability testing, and further prototype testing in the future. For those of you who are unfamiliar with environmental test chambers, they are used in various engineering industries to test the effects of specified environmental conditions on biological items, industrial products, materials, and electronic devices and components. An environmental test chamber can artificially replicate the conditions under which machinery, materials, devices, or components might be exposed to. Roscoe uses these test chambers to test the quality requirements of the products. This project arose because Roscoe has no system established to test the new product line, Project Semi, which is pictured in the upper right-hand corner. Currently, Roscoe has an outdated environmental testing procedure. The previous software that was used with the older environmental chamber model is not compatible with the new S-Spec Platonia Series chamber. Additionally, it lacks key functionality that would be necessary to test Project Semi switches. When looking at the present system, it was concluded that it was slow, unreliable, and incompatible for all products. Due to this, returns are increasing due to the lack of quality assurance. Throughout the duration of working on this project, I was able to apply some of the knowledge and skills I've learned in many of my classes here at Cal Poly. Within industrial engineering, just to touch a couple, I was able to use skills from IME 457, Advanced Electronics Manufacturing, IME 430, Quality Engineering, IME 405, Operations Research, and IME 312, Database Management and System Design. Outside of my major, I was able to apply concepts learned from EE 201, Electronic Circuit Theory, and EE 321, which is just electronics. Before beginning to work on a solution for this problem, a few assumptions need to be made. First being that NILabVIEW software will be utilized for the new system platform, and a Microsoft Access database will be used for long-term data collection. Following that, we plan to test between 50 and 100 switches. Next, the customer requires new product development to be tested within a temperature and humidity-capable environmental chamber, such as the one on the right. Following that, the chamber cannot achieve humidity functionality above 80 degrees Celsius due to the wick drying out. And lastly, pressure flow is distributed evenly throughout the manifold during all testing. This will make sense a little more down the road. When determining a systematic approach for this project, we decided to use a combination of two different types of methodologies. The first being crawl, walk, run. Crawl changes are immediate, with immediate benefits. They can be implemented easily and lay the groundwork for bigger, more impactful changes down the road. These also include configuring lower-level programs that work independently from one another. Walk changes are near-term. They have a longer time frame than the crawl changes, but they may include process changes, minor hardware and software upgrades, or consolidating various aspects of the crawl phase into a larger framework. While run changes are long-term objectives, these changes may include database implementation and organizational restructure or adoption of DAC devices. In this sequential methodology, you must crawl before you can walk, and you must walk before you can run. Within this system, DMAIC, define, measure, analyze, improve, control methodology can be applied at the various stages. In the define stage, the software developer begins his work by reviewing and understanding the design and requirement specifications from the user. These documents are essential for understanding user requirements and creating a framework for the software code. Then, in the measure stage, using an older environmental chamber program, current baselines for improvement are established. This will be the performance metric to compare at the conclusion of the project. In addition, be used as a low-level process flow baseline for the code. Following that, we have analyze. In the case the software development team is unable to understand user requirements correctly and further clarification is required, the deliverables are sent back to the user. In addition, the software development team also returns the requirements that are understood by them. Following, we have improve. After the requirements are clearly understood, the design and specifications are implemented in source code, which would be the main VI, the supporting files, which would be the sub-VIs, and the project library. In some cases, there may be a proposal of change in hardware or software specifications for program optimization. And finally, we have control. Here, software testing is carried out to detect and correct errors on each module and sub-VI of the software code. As part of the proposed solution, a user interface was developed for the operator to interact with. As you can see in the middle of the user interface, there is a flow process diagram which outlines the different states of the process, starting with initial venting, then moving on to idle, database, set temperature and humidity, wait for temperature and humidity, pressurizing, venting, and check cycle count. Here we can see the program in action. As you can see from the two graphs on the right, temperature and humidity are constantly being monitored. This gives the program an artificial-like intelligence so that if temperature and humidity ever fall outside of the given tolerance zone, the program becomes self-aware of the issue and then corrects itself. Along with temperature and humidity, pressure is also constantly being monitored. This is essential because when capturing the switch's actuation pressures, we are going to need the transducer value. Once your operator wishes to begin testing, he or she will then hit the Start Testing button. Once the button is pressed, you can see from the light indicators as the flow process diagram flips through the different states. First go into a database state, where the temperature and humidity are pulled from a database. Then the temperature and humidity are set in the set temperature and humidity state. Following that, the program will wait for the temperature and humidity to be set. Once these are set, the program will begin pressurizing and venting through the different cycles until the desired cycle count is achieved. The second tab in the user interface outlines the databases being used for testing. Here, the operator can see the table name, the part ID, and which current state is being used for testing. This can be useful for the operator to see how much of testing has passed and how much more testing there has to go. The third tab on the user interface shows the operator which units are being tested. This gives a visual representation on when the switches actually actuate. As we can see from the different switches labeled serial number 1, 2, and 3, we are able to see when the switch activates and deactivates. In the table below shows a visual representation of the data being pushed to the database. Here we have the actuation pressures all being pushed for the different switches being tested. When designing the structural code for this program, I decided to use a state machine. What a state machine does is uses a string of if-then statements to decide which following state to go to. For example, if the temperature and humidity have been set, then go to the wait for temperature and humidity state. Else, stay in this state. In total, there are 12 states that this project can cycle between. Within each state, we have what we call sub-VIs. Sub-VIs are programs that are made independently from the main program, then added to it later. For example, this sub-VI is a database sub-VI. Here, we write information to the database, and then that information is then relayed back into the main program. Flickering through the different operations of this, we can see many other different functionalities of this particular sub-VI. Information is passed into a case structure which indicates which operation to do. And then that information is then outputted back into the main program. Here we have more examples of the database VI. This information is constantly being monitored as to check whether the temperature and humidity are within specs. Again, if these fall out of specs, the temperature and humidity will eventually stop, correct itself, and then continue testing. Here we have the data acquisition sub-VI. This is where we monitor the actuation pressures of the different switches. To work in conjunction with the software, much hardware needed to be set up for this project. First, we have the PXIe, which is essentially the brains of the operation. The PXIe is an 8-modular rigid CPU. Connected to the PXIe, we have a terminal block. A terminal box is an extension of one of the digital I/Os for the CPU. Using the white 20-gauge wire, we connected the terminal box to a terminal block. This can be seen on top of the blue Aquamil bin. The terminal block acts as a convenient patch panel to connect the solenoid valves and the switches to the terminal box. The switches and the solenoid valves are controlled and monitored through the digital I/O of the DAC device, which is essentially the PXIe. Then, underneath the switches and solenoid valves, we have the power supply, which supplies 12 volts DC to the protoboard. Relay and transistors on the protoboard are then used to direct power to the solenoid valves, which give them the capabilities to function on and off. When doing an economic justification for this project, a 5-year cost-benefit analysis was performed. This analysis highlights the cost moving from a manual process that is labor-intensive to an automated process. One thing to note here is that for the old procedure, the engineers were the operators, and thus their time is more valuable, which means the old procedure would cost more. When analyzing the environmental impact of this project, the thing that stood out the most is that there is going to be less rework, which means less material scrapped. This is due to an increase in quality of the existing product from being tested and increased data collection used for the R&D iterative process. Another benefit of this project is that we are using all data collection using a database, rather than the old method, which was all done with paper. And finally, as determined through time studies, the new system is roughly 300% more effective in speed. This means that there is going to be less energy usage in the manufacturing process. The new system saves roughly 10 times the amount of kilowatts per hour with respect to the legacy system, due to it being 300% faster per test, and in addition to that, it can test 10 times the number of units per test with respect to the old legacy system. Although we still have a couple of weeks to finish this project, there are still some opportunities for improvement, one being greater scalability for the PXI 1045. This means creating software and hardware both able to withstand a scalability of 2 times the amount of the current system. That's for a total of 16 modules. Next, it will save a lot of time and setup time if a convenient patch panel can be made for the switch connectors and the pressure valves and plumbing. This will allow the operator to quickly connect all 100 switches without having to deal with a big bundle of wire, as you can see in the bottom left, moving from a system like that to one in the top right, where it's more of a plug-and-chug type system. In closeout of this project, the final deliverables are as followed. A high-speed test and measurement system using NI software that has the following functionalities: lifecycle testing, environmental testing, accuracy and repeatability testing, automatic data acquisition of pressure switches, actuation pressures, using database connectivity. In addition to that will be an ergonomic server rack that the operator can use without ease. Well, that concludes my senior project overview. I'd like to say thank you for taking the time for watching this video, and I look forward to seeing all of you IAB members at the Project Expo.